Hey everyone, welcome back to physics. This will be lecture 23 of the course. And in this section, we're going to just wrap up sort of chapter 4, applying Newton's laws, with some final examples. A few final examples just kind of round out a few items that we maybe haven't, a few scenarios that we haven't seen. So let's go ahead and jump into it. We'll call this section 4.6, problems and examples, of course, applying Newton's laws. So I've got 3 examples that I want to look at, each of which are similar to problems that we did as per the normal lectures in the section, but each of them a little bit different, just involving a few little items that we maybe haven't seen. Okay, and also this will be a slightly shorter problems and examples just because we did so many problems and examples in the previous section. So let's go ahead and take a look at the first one. So the first example says a crate with a mass of 50 kilograms, crate with a mass of 50 kilograms is sitting on a rough inclined plane. Sitting on a rough inclined plane. And this inclined plane makes a 30-degree angle with the horizontal. Makes a 30-degree angle with the horizontal. Okay, now there's friction between the plane and the crate, and that friction, the kinetic friction coefficient for that is 0.2. So mu sub k is equal to 0.2, right? And that's between the crate and the inclined plane. Now a worker pulls the crate up the incline with a force of 400 newtons. 400 newtons parallel to the plane. Okay, now the questions are, there's 2 of them, we kind of go together. First, we want to find the net force acting on the crate. Find the net force acting on the crate. Okay, so what's the force acting on the crate? You got it pulling it, there's weight, there's friction. What's the net force? And then secondly, what's the acceleration of the crate as it moves up the plane? What is the acceleration of the crate as it moves up the plane? Okay, all right, so seemingly simple, and well, I mean not a crazy hard problem, but I don't know that we looked at scenarios quite like this where you've got masses moving at up-angled planes where a lot of friction is involved. Okay, so let's take a look at this. Obviously, physically, what's going on here is I've got some kind of a plane, 30 degrees, and I've got this crate with a 50 kilogram mass that's being pulled up this plane. And so we just want to really what we're interested in is we want to know the acceleration of this thing if I apply a certain force parallel to the plane. Okay. And so in the most basic sense, you can think about the free body diagram basically looking like this. I've got the crate. The weight of the crate is pulling it straight down. All right, mass times gravity. I'm pulling it up the plane, so there's this pull force that's operating parallel to the plane. And then, of course, you've got the normal force, which is at a different angle. Well, it's acting perpendicular to the plane, right? So it's not aligned with the weight of the crate. Okay. And so what we'll probably want to do here is we got to figure out how to lay in the coordinates appropriately. right? We have to think through. I think what we should do is make this the x coordinate, right? The x-axis, and then this will be the y-axis. So the normal force and the pull are perpendicular to one another. The odd man out here is the weight. And so the way I would want to think about it is let's break the weight down into its x and y components, right? So we'll have like wy here and wx here. Okay. And so this is an exercise you've seen. This will be the 30-degree angle right there. And so we can break this down. Now really, once we do that, once we recast some of these forces along the x and y axes, the chosen coordinatization of x and y, the free body diagram is going to look a bit more like this, right? So you've got your normal force, or sorry, you've got your pull force pulling like this, and we'll say that's 400 newtons. We're given that. And then technically you've got the weight kind of coming down like this, but really it's going to have two components. There's going to be this one here, which we'll call wy. And then there's this one here, which we'll call wx. So some portion of the weight of the object is being pulled perpendicular to the pulling force, and some portion of the weight of the object is pulling in line with the pulling force. Right, so you've got the weight kind of pulling this way and pulling that way, and then the sum of those two are the overall weight. Then, of course, the normal force is going to be like this, right? So this way you can see that the y component of the weight of the object is in alignment with the normal force. That's how the normal force works. It opposes the force. It is opposite and equal to whatever this force pulling the object into the plane is. And then you've got the weight of the object also trying to pull it back down the hill, right? Some small portion of the weight anyways. Now the one force we don't have on here yet actually is the friction force, because friction is operating as well, and it's going to operate opposite the pull force. And so I'm going to put it down here like this. It's kinetic friction because the object's assumed to be moving, and so you've got the force of kinetic friction like that. Okay, so this is the simple free body diagram, and I guess I should have had friction on there as well. And then you take the weight of the object and you kind of, break it apart, and now you've got this nice free body diagram where everything is along the x and y axes, and so you can align everything. Okay. So once you kind of conceptually place the thing and kind of derive this kind of a free body diagram, it's fairly straightforward. Let's go ahead and figure out what all the quantities are that are involved here. So I've got the weight of the object. That's equal to the mass times gravitational acceleration, which is 50 kilograms times 9.8 meters per second squared. And so when you multiply those together, you see that the weight force is 490 newtons. Now that force can be broken out along, again, the x component and the y component of the weight force, right? And so we'll do wx first. That's equal to 490 newtons. Now you can just draw a triangle off to the side to figure out the sine and cosine piece of this, but this will be times the sine of 30 degrees. Okay, when you do that, you get 245 newtons. And wy is similar, 490 newtons, but cosine of 30 degrees. And when you do that, you see you get 424 newtons. Okay, and that should align with your expectations. I mean, this isn't a super steep incline, right? The majority of the weight is still heading, is kind of pulling it down into the surface. Only a fraction of it is actually pulling it down the surface, right? So you can see that difference here between these two values. Once we have the weight in the y direction, we can derive the normal force, which is just going to be equal to that. So the normal force would be 424 newtons, same as w sub y. And then the friction force is a function of the normal force, right? So F sub k will be equal to the magnitude of the normal force times the coefficient of kinetic friction. So 424 newtons times 0.2. Okay. and that gives you 84 newtons. All right, so we've got all of the pieces here. All right, so there's really no net force in the y direction, right? The crate is not accelerating through the surface of the plane, right? It's just stuck on top of there. So W sub y and the normal force are in perfect alignment. So really what we're interested in is the x direction. So what's going on in the x direction? So the sum of the forces in the x direction, what are they? Well, you've got negative W sub x minus F sub k, sorry about that, minus F sub k, and then plus F sub pole, right? So you've got this guy, and that guy, those three forces acting sometimes in concert and sometimes opposite. And these are all known quantities, so we can just plug the values in. So negative 245 newtons minus 84 newtons for the kinetic friction plus 400 newtons, that's the pole force. Add all of those up and you'll see that the net force is 71 newtons, right? So there is a net force in the x direction of 71 newtons, which means the crate will be accelerating up the plane. Okay, and so what is that acceleration? Well, the acceleration, remember, is found simply using Newton's second law. Sum of the forces in the x direction is equal to the mass of the object times the acceleration in the x direction. So we know the sum of the forces, we know the mass, so we can solve for the acceleration. A sub x will be equal to the sum of the forces in the x direction divided by the mass. And we see, what, 71 newtons divided by 50 kilograms. And so we should see an acceleration of about 1.42 meters per second squared. All right, very good. So that's a nice example of using Newton's second law and figuring out what is happening with a crate when there are friction forces operating on it. Okay, the second example is going to be a uniform circular motion style example. So let's take a look at that one. Okay, so what do we got going on here? We got a car with a mass of 1,200 kilograms. A car with a mass of 1,200 kilograms is moving around a flat circular corner of radius 50 meters. Is moving around a flat, right? So no incline. A flat circular corner of radius 50 meters. Okay. The coefficient of static friction between the tires and the road is 0.6. So I'm just going to put mu sub s equals 0.6. And that's understood to be between the tires and the road. Okay. All right. Let's assume the car does not slide. Assume the car does not slide and moves in uniform circular motion. What does that mean again? Well, it means that it's, first of all, it's a circular path. It's an arc of a circle that the car is moving around, and also the speed of the car is fixed, it's constant. All right, so uniform circular motion. So assume the car does not slide and moves in uniform circular motion. Question is, what is the max speed? What is the max speed the car can have as it rounds the corner before it starts skidding? Okay, so you've got this car racing around this flat corner, right? So there's no funny business with the normal force, right? You got this car racing around this flat corner. There's a certain amount of friction between the tires and the road. The question is, how fast can this thing go around this corner before it starts skidding? Okay, so let's draw some pictures here. This is the top-down view. I got this corner, and r is equal to 50 meters, so it's some radius here. And I got this car racing around the corner. Right, it's just heading around this corner. It's got a certain velocity. We don't know what that velocity is. That's really what we're trying to figure out. How fast can this thing go before it starts to skid out? Now let's look at a free body diagram of the forces involved. So I'm going to kind of draw the car just so you can tell what perspective I'm using. So I'm kind of using a head-on perspective of the car. Right, so I got the car kind of like this. Right now the car's got a weight pulling it down. It's got a normal force that is perfectly aligned with the weight, right? It's a flat track. Previously, we've seen examples where there's an incline to the track, and so the normal force is not aligned with the weight of the car. But in this case, it is. And then I've got a force that's sort of pulling the car off the track, and that force is countered by static friction between the tires and the road. Right? So the car is racing around the track, the static friction keeps it on the road, this other force is trying to push it off the road. Okay, so in order for the car to not skid off the road, this force that's pushing it, trying to push the car out of the corner, must be less than or equal to the maximum static friction value. Okay, so in order to keep the car on the road, the magnitude of the force trying to push the car off the road needs to be less than or equal to the static friction force, like the max. Okay. And remember, this static friction force max is really just the normal force times the static friction coefficient. Right. Remember that the static friction will increase up to this value, up to magnitude of n times mu sub s. Okay, so that's all you really need to know. And once you've kind of got that, it's a matter of kind of, calculate all the quantities and set up the appropriate expression. So what's the weight of the car? Mass times gravity here is what? 1,200 kilograms times 9.8 meters per second squared. That's pretty heavy, significant force there, 11,760 newtons. Okay. And so if that's the weight, then that's the normal force also, right, in opposite direction, but the magnitude anyways is also 11,760. Okay, so what's the max static friction force? Well, it's going to be equal to this normal force times mu sub s, and so 11,760 newtons times 0.6. So about 7,065 or 7,056 newtons. Right, so once the force pushing the car off the road exceeds this value, then the car will start to slide off the road. Okay. Now there's nothing to worry about in the y direction. We've got equilibrium there. We're really interested in the interplay between these two forces. Right, and so what we have is the sum of the forces in the x direction needs to equal the mass times the acceleration in the x direction. Okay, now we're talking uniform circular motion, right? So the direction here, the acceleration, this force vector is always in the direction of the radial acceleration, right? And so we can set this thing here equal to mass times another way to express radial acceleration, a rad, here is v squared over r. Okay. Okay, and so really we need all of this to equal, to net out, right? Okay, and so what do we have here? We'll say 7,056 newtons, right? That's the max static friction force. That needs to equal m times v squared over r. Okay, and then we can just solve for the maximum velocity. We can figure out what that velocity is, and that's going to tell us just how fast we can go before we start to skid. So v squared should equal 7,056 newtons times the radius of the circle divided by the mass of the object, or the car. And so V will be just the square root of that. So 7056 newtons times 50 meters divided by 1200 kilograms. Right, so you got newtons over kilograms, and then you got an extra meter in there, so this is all going to be meters per second afterwards, right? And so what do we get? We get, when we multiply all of that together, we get about 17.1 meters per second. Okay? Perfect. All right. So that is basically the car can race around this corner at max 17.1 meters per second squared. As soon as, if you go 17.2 meters per second, this thing's going to start to slide, and then it's going to slide more the faster you go. But up to this velocity, up to this speed, the car should be stable around this particular corner with this particular car, etc., and these particular tires. So very good. So that's a nice example of using Newton's second law to identify a max speed around a flat corner. Okay, let's do one more example, and this one will be a little bit trickier. It's something we actually haven't seen. Okay, and so let's write the problem out here. So this is a problem type we haven't actually, well, we've seen kind of aspects of this, but not this kind of problem explicitly. So this one is going to involve a house painter and some contraption that he's designed, that he built, that he uses to, climb up the side of the house. So a house painter uses a chair and pulley arrangement. A house painter uses a chair and pulley arrangement to lift himself up the side of a house. Okay. The painter's mass is 73 kilograms, and the chair's mass is 9 kilograms. Okay, so you've got this painter who's sitting on this chair, and it's like attached to this rope with a pulley, and he uses it to pull himself up. And we'll draw a picture in a second. Now here's the question. The question is, with what force must he pull down? With what force must he pull down on the rope in order to accelerate upwards? In order to accelerate upwards at 0.25 meters per second squared. Okay, so what the heck is going on here? All right, so we've got this rope. Right? Well, we've got this pulley, right? This pulley at the top here. And attached to it is a rope, which is attached to some kind of a contraption that the painter is standing on. Okay, so you've got this painter, and then he is pulling down on the rope that goes through the pulley, right? So this guy pulls down on the rope, and it pulls him and the chair upward. Okay. All right, so this is kind of a weird problem. It almost looks like it shouldn't work, right? But it does work. It does work. And so because there's a number of things involved here, let's kind of think through the different objects that are involved. So we've got the painter and the chair. Let's start with that. Right? Now there's this interaction between the painter and the chair, basically the normal force, right? The chair pushes up on the painter, and the painter pushes down on the chair, right? You think of those as equal and opposite. That's an action-reaction pair, right? Okay. Now, there's also the earth, right? Gravity. I'm going to write earth down here. So earth is pulling the chair down. We'll call that, its weight. And it's also pulling the painter down. We'll call that weight also. Okay. Now, the other thing that's happening here is you've got the tension in the rope that's kind of holding the whole apparatus up. And so the tension is actually operating on the chair, and it's operating on the painter. Okay, now this whole apparatus is moving in unison, right? The chair and the painter move in unison. One doesn't accelerate more than the other. They both accelerate together, right? So you can kind of think of them as a single body. Right? You really can think of them as a single body, given the fact that this is an action-reaction pair between them. Okay, so what does Newton's law say? Well, first of all, okay, so this is kind of the setup, right? Let's kind of separately write out free body diagrams for the painter and the chair, because the way we're gonna solve this is we're gonna develop second law equations for both of them separately and use them together. So for the painter, what's going on here? So here's the painter. Well, you got the weight pulling the painter down. I'm going to denote it with a P there. And then you've got the tension in the rope holding the painter up. Right? And then you've also got the normal force between the chair and the painter pushing the painter up. Chair pushes back on the painter, painter pushes down the chair. All right, so that's what's happening with the painter. What's going on with the chair? Well, similarly, you've got the weight of the chair. Right? Gravity's pulling it downwards. You've also got a little bit of a normal force, the painter pushing down on the chair. Now, these two forces here are the same, aren't they? Just in opposite directions. Action-reaction pair. And then you've also got the tension in the rope holding the whole thing up. Okay. So then let's set up a couple of equations using Newton's second law. Now all of this is in the y direction, right? There's no x component to worry about in this case. So everything's in the y direction. So let's set up a couple of equations. We'll start with the painter. All right, so the sum of the forces acting on the painter in the y direction would just be equal to the normal force, right, pushing up, plus the tension force pushing up, minus the weight force in the case of the painter pushing down. And that's going to be equal to the mass of the painter times the acceleration. Okay, that's what's happening with the painter. What about the chair? The sum of the forces operating on the chair would be equal to, well, you got the normal force pushing down, so I'm going to put negative n. Then you've got the tension force pushing up. And then you've got the weight of the chair minus WC, and that's all equal to the mass of the chair times the acceleration. So if we look closely at this, what quantities do we know? What quantities do we not know? Well, we know the weights, right? We're given the mass, and we can calculate the weights. So really, we know these three. We know those three. We also know that these normal forces are the same, right? So a good approach to this might be to, what we're really interested in, the force we're targeting is the tension force, right? We want to know that represents how hard the painter pulls down on the rope, is that tension. That's what he creates the tension, right? Okay, so tension is the force we're targeting. We know all of the quantities except the tension and the normal force, so let's just solve for t and plug in n from the other one, right? First, let's figure out what all these quantities are. What is the weight of the painter? Well, it's the mass of the painter times gravity. And so it's 73 times 9.8. I'm leaving the units off just because this will get a little messy otherwise. But you know this is kilograms. That's meters per second squared. And so we get 715.4 newtons. That's the weight of the painter. The weight of the chair is the mass of the chair times gravity. So that's 9 times 9.8. And so there we get 88.2 newtons. Okay, so we've got these two. All right, so let's plug this in. We'll call this equation 1, and this will be equation 2. So For equation 1, we have the normal force plus the tension force minus 715.4 newtons is equal to 73 kilograms times, what's the desired acceleration? 0.25, right? 0.25 meters per second squared. Okay, so there's 1. For 2, we've got negative normal force plus tension force minus 88.2 newtons. That needs to equal 9 kilograms times 0.25 meters per second squared. Okay, so I'm going to solve for tension here in the first equation. Okay, so tension is equal to 715.4 newtons plus 73 kilograms times 0.25 meters per second squared, so that's this, and this, then minus whatever that normal force happens to be. Okay, now for 2, I'm going to solve for the normal force so that I can plug it into this thing. So the normal force is equal to, just rearranging some stuff, it's going to be equal to the tension force minus 88.2 newtons minus 9 kilograms times 0.25 meters per second squared. Okay, now I'm just going to take this thing here, plug it in there, and that'll give us the tension, right? All right, so the tension is equal to, so all of this stuff here, 715.4 plus this, that's 824, oh, sorry, let me, no, that's equal to 733 newtons. So I'm just going to write that. Okay, so that's this whole thing. And then minus this normal force, right? Minus that. So that's going to be minus, plugging all this in, T minus 88.2 newtons minus 9 kilograms times 0.25 meters per second squared. Okay. And then I get 733 newtons minus T plus 88.2 newtons, and then plus, what is this? This is 2 1/4. 2.25 newtons. All right, so I've got T over here and minus T over there. That means I've really got 2T, don't I? Right, and so then I take 733 plus 88.2 plus 2 1/4, and I get a total of 824 newtons. Okay, and so that means the tension force is equal to 824.1 newtons divided by 2, which happens to be 412.05 newtons. All right, so what does that tell us? Well, the weight of the painter is 700 newtons, and this guy's got to pull down on the rope with 400 newtons of force to get him, to make him accelerate up the wall at the desired pace. So this just seems amazing, right? Because I think why this seems so fascinating is because, like, look, as he pulls down on the rope, he's actually lifting himself up a little bit, isn't he? His weight is in flux a bit, right? He's also pulling up on the chair, and so why doesn't he have to lift his whole body weight, right? Exactly. That's the thing that makes it seem kind of remarkable. Right, and he doesn't have to lift his whole weight plus the chair. He just has to pull with 412 newtons of force, roughly 2/3 of his body weight, to get himself to accelerate upwards. So whenever you see these guys hanging off the side of buildings, washing windows, and they're sitting on these chairs, know that they have to pull a fair amount to get up to where they're at, but the physics is such that they don't have to lift themselves entirely, only a fraction of themselves. Right, and of course it depends on the pulley setup too, right? So if you modify this pulley in certain ways, the amount of force required to lift oneself can change as well, can be made significantly smaller in particular. All right, very good, very good. So that's kind of an interesting problem, a little bit counterintuitive. But I'm sure you've seen these kinds of phenomenon in the real world, and maybe now you can, when you see it, you'll know. Oh, there's a physical reason that they do it that way, not just so they can sit on that, but actually helps them get up the wall with a little less effort. All right, so that's where we'll leave it. Now, when we pick up in the next section, we'll start to talk about. We'll be shifting gears somewhat, and we'll start to talk about work and energy. Particularly, I think work and kinetic energy comes next. So until then, take care.